In this lecture, we will derive the point form as well as the conventional form of Ohm's law in ohmic media. Now, let us say that there are n charge carriers per unit volume, and that each charge carrier is having q coulombs charge on it. So the charge per unit volume is going to be nq. Now, if I assume that each charge carrier is having an average drift velocity of u, so the total current passing through a surface area in the direction of this drift velocity is going to be given by this quantity, that is coulomb per meter cube into meter over per second over second. So it is going to give us coulomb per second per meter square, that is ampere per meter square. So this is going to be the current density. Now, in my previous lecture, I have shown how we can calculate current from current density. Let us say that this is a surface area and some current density is flowing through this surface area, that is charge carriers are flowing. The average drift velocity is in this direction like this. So to find the total charge which is going to cross through this area, now we know that this velocity can be broken into two components. The first component, which is along the surface, and the other component which is perpendicular to the surface. Or if I want to draw it in 3D, I will have to draw it like this, something like this. This is the plane of this. This is the plane, and this is the velocity. So it will have one component along the plane and other component along the normal of the plane, if this is the normal. So you should try to imagine in 3D that this component which is along the plane is not going to create any charge across the surface, that is which should pass through the surface. It will just pass along the surface. Only the component which is along the normal of this surface is going to pass through this surface. So the velocity and its component along the normal of this surface is going to give that part. That's why to find the current passing through the surface, we need to get the dot product. So this was called as the volume current density, and this is going to give us the current passing through that surface area. So this vector volume current density is valid at every point, that is it is having magnitude as well as direction at every point. So this is a point function. However, we cannot say the same thing for the current, because for current we need to have an area across which the charge should pass for a given amount of time. So current is not a point function, or that's why we cannot define it at at every point. For that we need at least some surface area through which the charge should pass. So that's why this is a vector quantity and it is a point function vector. However, this current is usually called a scalar, and we can see that it is actually a dot product of two vectors, the area vector and the current density vector. Of course, its direction depends on the orientation of the normal of this vector, or the normal of the surface vector. Now, in many material, especially semiconductors, there can be two types of charge carriers, and in some material, let us say there are some other kind of charge carriers, ions are also there, which are having some possibility of movement. Then there will be current density because of the movement of all kinds of those charge carriers. So I will assume that Ni is the charge density of ith type of charge carrier, and Qi is the charge on each type of the charge carrier, and Ui is the velocity of drift velocity of each kind of charge carrier. So the total volume density will be because of the vector sum of all types of the charge carriers. That is volume current density because of electron motion, volume charge current density because of hole motion, volume current density because of ion motion, and so on. So to find the total volume current density, we need to find the volume current density of every kind of charge carrier. Now, especially in conduction currents, which is typically in conductors or metallic conductors, this drift velocity, and usually the charge carriers are electron in them, and they are having charge minus E. Every electron is going to have charge minus 1.602 10 to the power minus 19 coulomb. So E is equal to 1.602. So minus E is the charge on each electron. And we can show that the drift velocity of electrons on an average is proportional to the electric field. Now, this electric field is not the applied field, it is the resultant field. That is applied plus effect of other charge carriers. So we can write that this drift velocity is equal to minus of mu E, where this is called as mobility of electrons. Which is having a unit of meter square volt per volt second. Now, its value varies from material to material. Like for copper, the electron mobility is around 3.2 into 10 to the power minus 3 meter square per volt second. For aluminium, it is just 1.4, less than half, or rather one order low as compared to copper. So you see, for different kind of material, it is going to have different value. Now, putting this thing, we know J is equal to NEU, and for electrons, charge is minus E, so J is equal to minus NEU minus NE. Now U is equal to minus of mu E. Now I can write it as NE mu E. Now this quantity is called as sigma, or the conductivity. That is the charge per unit volume, which is equal to NE, where N is the number of charge carriers per unit volume. So its unit will be per meter cube, and this is in coulomb. So the charge per unit volume into the mobility is another factor which is depending on the material, because this thing as well as this thing is going to depend on the material. So J is equal to sigma E, but the current density is proportional to the electric field. So this is a linear equation. Although this proportionality constant is going to vary with the material, and it will depend on the material as well as of course temperature also, and the dependence of this sigma or the conductivity on temperature is much more as compared to the dielectric constant dependability on the temperature. So we find various issues in deriving governing equations because there is an effect of temperature also whenever we have to consider this sigma. Now, as I have told, if there are more than one kind of charge carrier, this sigma will be consisting of the conductivity because of each type of charge carrier. So as I have told, that sigma is actually equal to Ne mu E for electron. Similarly, for hole, it will be equal to Ne. So let us say this is minus plus, just showing the difference in concentration. Although this quantity is always positive, this is just number of charge carrier per unit volume, U holes. Similarly for ions, Anion, Eu. So for a material which is having both electron as well as hole, so this is going to be the sum of both Ne mu E plus N hole. I am assuming each hole is having the same charge as that of an electron. Now, typically the value of this mobility for electron and hole are totally different, and holes are having lesser mobility as compared to the electrons because of various reasons having physics behind them. Now, this equation J is equal to sigma E is sometimes called the constitutive relation. and it is valid at every point in the medium, conducting medium. And the media which are going to follow this equation are called as ohmic media. Like copper is having a value of this conductivity as 5.8 into 10 raised to power 7 Siemens per meter. Now, sometimes we deal with the reciprocal of sigma, and that is called as resistivity. So there is no, speciality about using equation in this form or this form. So we will use these interchangeably in our study. As I told, that sigma is much more dependent on the temperature variation as compared to the dielectrics, where this epsilon r was not depending that much on the temperature. So conductivity of materials, they vary a lot and over a wide region with temperature. And for semiconductors, we usually find that conductivity increases with the increase in temperature. For normal kind of conductors, we see that conductivity decreases with increase in temperature. So these have an issue of thermal runaway because it leads to a positive feedback system. Now we will try to derive the conventional form of the Ohm's law. This is the point form because it is valid at every point in the media. Now to prove that, let us take a conductor having a uniform surface area, cross section surface area, although I am not able to draw uniformly it everywhere. So let us say this is a uniform cross section area, and the electric field inside it is E. So as I have told, J is equal to sigma E, since it is a conductor and follows this relation. So J is going to be in the same direction as that of E. Now let us say this is positive, this is negative, and the potential difference between these two will be, let us say this is terminal 1, this is surface area 2. So this will be equal to V12. So let us say this is length L. So the potential difference between these two will be equal to minus of E dot dl from 2 to 1. Now this dl is in this direction, E is in this direction. So E dot dl will be negative, but this negative will get cancelled out because of this. So it is going to give us E dl from 2 to 1, and it is going to give us EL, assuming E is uniform. That is, sigma is not going to vary and the current is uniform across the conductor. Across whole conductor, the current density is not going to vary because we are assuming steady conduction. So current along any surface area, because we have taken surface area uniform across the whole length, so this is same. So E is also same, and we have taken it outside the integral, and this is equal to EL. So V12 is equal to EL, or E is equal to V12 by L. Now we know that current is just the integral of the current density over the surface area. So as I have told that the current density is uniform across the surface, so it is just Js, where S is the surface area of this cross section. So I by S is equal to J is equal to sigma E is equal to sigma V by L. So V12. So V12 is going to be equal to L by S sigma I, or 1 by sigma can be written as rho, the resistivity, L by S I. So you see, this quantity is depending on the material as well as the dimension of the conducting medium. So this is called as resistance. So we can write it as V12 is equal to Ri. So for a given conductor, or depending on the shape of course, for a given type of conductor and geometry, the voltage across it is, voltage across the terminal is proportional to the current through it. That proportionality constant is R. Now as I've told that this depends on sigma as well as the geometry, and thus it depends on the temperature. So this equation is valid as long as we do not vary the temperature. For a given temperature, this equation is going to hold. And this is, of course, we have also assumed that the media is homogeneous, means sigma is not varying along the media. So for a steady steady conduction problem in a homogeneous media, we can write V12 is equal to Ri, and this is the conventional form of Ohm's law. So in this way, we have derived this Ohm's law, although it was discovered experimentally first, I believe. This is the conventional form, and this is the point form of the Ohm's law, which is valid at every point in the medium. If we know sigma at every point, it will be even valid if the conductivity is varying from point to point. So if you find that this lecture is helpful to you, then please share and subscribe our YouTube channel, and also join our Telegram group, whose link is given in the description of this video. Thank you.